This is the first class in the online virtual international oral piano tuning conference. I want to thank you all for coming, and also I want to welcome Robert here, who's going to be in the chat. If there's any questions, that it's a small class. I don't mind if you interrupt for any questions, but if you have something that you don't want to interrupt me with, you just want to type it away in the chat, then Robert's going to be there, and he's gone through the course already, so he's pretty knowledgeable about the elements of it, and he'll be able to answer your questions, and any he can't answer, he'll send them on to me. So this class is on just basic piano tuning theory. And the topics we're going to talk about today are naming notes for piano technicians. So there's a different way of naming the notes. It's a simpler way than classical music theory. It doesn't mean you can't use classical music theory to name notes. It just means if you have a little bit of, if it's a challenge for you, the classic music theory, maybe you never got the theory when you were younger, then this is a perfectly fine way to do it. Same thing with naming intervals. Then we're going to talk about the harmonic series, beats in piano tuning, coincident partials, pure, wide, and narrow intervals, equal temperament, check notes, inharmonicity, and octave sizes. So naming notes for piano technicians. Piano technicians need to know what note they are tuning and what note to tune next. That's it. So we get into some confusion when sometimes we have this, with classical music theory, there's sometimes a conflict about the way some piano technicians name notes and intervals, and classic music theory dictates it should be named. But we really want to know what note to tune and what note to tune next. Sometimes when I'm talking and teaching with other technicians, some who have been tuning for longer than I have, they get a little frustrated, and they have a right to be frustrated if they get confused by some of the things we're talking about, like things that maybe they figure they don't really need to know, right? And in this case, there's a bit of, they could probably have an argument there that you don't really need to know the classic music theory. For example, if you want to tune a piano, all you really need to know is what note to tune and what note to tune next. Well, we could just use numbers. You could just say, tune note 49, and then go down 12 notes and tune note 37 from note 49, and then go down another 4 notes and tune note 33 from note 37 to 7 beats per second. But because many piano technicians are also musicians, the tradition of using actual musical terms has been used. The problem is, many piano technicians are not professional musicians and don't want or need to compose or arrange music or be jazz musicians, which are traditionally activities that are highly require you to understand the music theory. To perform those skills, the composing, the arranging, playing jazz, it requires years of training to understand classical music theory, which is a sophisticated way of naming musical notes and intervals. Now, it's a good idea to acquire this skill if you have the time and interest. It can help you become a better musician. But many piano technicians don't need these skills or have the time to get good at music theory. All they want and need to know is, what note am I tuning? What note do I tune next? That's it. So we use the idea of naming notes and intervals with labels, like the numbers idea, but with names instead. This naming idea produces two things that go against classical music theory. Each note only has one name, and each interval only has one name. This simplifies the whole idea of knowing which note to tune and which note to tune next, but it does produce problems with classical music theory. For example, in classical music theory, each note can have multiple names. This note here is an E sharp and an F. Also, intervals can have more than one name. You're looking at this interval here. It could be a perfect fourth or an augmented third.
Mark, you're not sharing your screen.
Thanks. That must have been a little frustrating for you. All right, so let's just go from, I'll just continue on here because I think there was nothing you needed to see with what I was saying. This note here, E sharp and F, it's the same name, same note, I mean, different names. This interval here is a perfect fourth, but also can be called an augmented third. In music theory for piano technicians, which is it's like what this is called, this whole idea of how we're naming these notes, we only have one name for each note and interval. And this comes from these following rules. One, we don't use flats, we only use sharps. Now, some people have an issue with this, and I certainly accept that and recognize it. However, if you are a good musician, you should not have a problem with naming these notes as sharps. You know, if you feel so strongly about music theory and you have a really good grasp of it, it's not a leap just to say, okay, we're just naming these, giving these notes a name, and it might not agree with the classical music theory, but it works because it's less confusing. So we have an F and an F sharp. D, D sharp, C, C sharp, no flats. Secondly, we add numbers starting at 0, changing every C. So the bottom note A0, A sharp 0, B 0, then we have C1, C2, C3, middle C is called C4, and A4 the note where we usually start tuning when we're tuning by ear. And each interval is named based on the number of notes between the interval notes. That's it. It's very simple that way. And really, for some people who are trying to learn to tune pianos, they just want to learn how to tune. They don't want, if they're weak in the music theory, they don't want to have to struggle. So if you use this method, there's no struggle at all. This brings us to the intervals for piano technicians. So very simply, without going into any talk of major scales, we say a minor third has a symbol of a small m3, and it's 3 notes, where we don't count the first note. So you start on this note, count 3, you got a minor third. Now, what I like about this is that I haven't even named any notes. I've just played them. We're not naming notes. And when you think of the holistic way of performing and even tuning, the notes are kind of like back there somewhere. What's really in front of us is the piano. So here you see the minor third, up 3 notes, minor third. Major third is 4 notes. There's a couple of major thirds. The perfect fourth, 5 notes. Simple as that. Perfect fifth, 7 notes. We don't even know the note names. We don't need to know them. Minor sixth, 8 notes. Major sixth, 9 notes. And now I want to talk a little bit about picture patterns. So when we're playing the piano, we can imagine these intervals and what they look like. For example, the minor third. The minor third, half the time, is a black key and a white key, and the other half, the keys are the same color. So mixed colors would be like this minor third and this minor third. But when we get to the same color intervals, we have these 3 right? And these three. So it's like, it's simple when you see a pattern. It makes things simpler. Major thirds, we have now 8 black and white and only 4 that are the same color. The 4 that are the same color is CE, and then these 3. Those are all major thirds. If you recognize the pattern, it makes them so much easier to play. Fourths are even more amazing. It's 10 that are the same color. Starting on GC, all of these fourths, same color, taller fourths. Where do we start on GC? And then for the next 2, that's where you do the switch off like that. Same thing with the fifths. Starting on C and G, all the same color, except here, these last 2. Inversions can help us figure out note names because the minor third is just the inversion of the major sixth. You take a minor third, take the bottom note, bring it up to the top, it's major sixth. Same thing with the top note. Bring it down, major sixth. The major third and the minor sixth are also inversions. Bottom up turns a major third into a minor sixth. Top down turns a major third into a minor sixth. And with the fourth and the fifth, those are also inversions. So this can help. Compound intervals are intervals that are larger than an octave. So if we have an octave here. Then for the 10th, we can talk about the major 10th, which is an octave and a major third. You start with the octave, add a major third, there's your 10th. The 11th is an octave and a perfect fourth. The 12th, and these are intervals that we will talk about. I'm not, like for example, the intervals we talked about, we didn't talk about a major second, we didn't talk about a minor seventh, because these are generally not intervals that are talked about commonly in piano tuning theory. That's what this course is about, piano tuning theory. So the 12th, the octave plus 7 semitones, or a fifth. And a 15th, a perfect 15th is just 2 octaves. A 19th is 2 octaves and a fifth. And the 22nd, the perfect 22nd is just 3 octaves. So there's the 22nd. So I'm going to put all of these slides into a PDF, and you'll get a copy of these, and this will be one of them that you might find useful. All the different intervals and the number of notes and semitones they are. So the next thing, before we do that, are there any questions about naming notes or intervals?
No.
All right. So the harmonic series. Whenever a note is played, a series of frequencies is produced, not just the frequency of the fundamental note, but a series of frequencies above the fundamental. And these frequencies have a pattern. The first extra frequency produced is an octave above the fundamental. So if we have D3, the frequency heard above that, the first one is D4, an octave. Okay. Now, the harmonic series is something that's very simple for people to know if they've already learned about it, but it can be a little tricky, and I have a little trick for you so that it makes it easier for you to learn this, okay? It helps to memorize the series if we think in octaves, 3 octaves. So the first octave is just that. It's just the 2 notes. The second octave is just the octave notes, plus a fifth in there. And then the third octave contains those octave notes, plus what we call a 7th chord. So that's it. There are other ways to explain the seventh chord, but if you look here, I just say think of notes 1, 5, 8, and 11, counting the bottom as 1, which is very simple, but not very useful if you're going to do composing, arranging, or playing jazz. It's only useful for piano. So this is the harmonic series above D3. I'll just play it so you know what I'm saying here. The octave, like, it's good to think musically, right? The second one, if you play any piano, you've played that pattern before. And the third one is that's the seventh chord. So when you play D7, D3, all of those frequencies are being played at the same time. And I'll show you later a little demonstration of that. They go on forever, but we're just looking at the first 8. So the harmonic series are frequencies that are harmonic with the first frequency, often called the fundamental. For example, if the bottom one here is 150 hertz, and now if you don't know, hertz is a measure of how fast something vibrates. 1 hertz is 1 cycle per second. So that's 150. The second harmonic will be just twice the fundamental. 150 times 2, 300. And the third, 150 times 3. And that's what you get. You get all of these numbers, which are just multiples of 150. But in real life, these frequencies are not this perfect, especially on the piano. They're a little off. So for that reason, we can't call these harmonics. We call them notes in the partial series. Okay, that's a difference between harmonic series and partial series. Now let me demonstrate the partial series. If you play the D, but don't let it play down, now you can staccato all of the notes in that series. You hear it ringing, but that ringing is coming from the D3. I staccatoed the D4, but when I let go of the D3, the note stopped. Why? Because the note is not coming from the D4. So just pressing down, lift up, the D3 stops ringing. And to prove that it's not some kind of a magic trick, I will press the D3 down and I'll whack the D sharp. Nothing. The C sharp? Nothing. Why? Because those notes are not part of the harmonic series, of the partial series of D3. So the notes in the D3 partial series, all of those, when I let go, they disappear. That's one demonstration. Another demonstration we can show with the guitar. Let me just see if I can make this a little bigger. Okay, so the harmonics can be found by cutting the string into even pieces. That's the fundamental. At the 12th fret, we're cutting it in half. And then the 7th, cutting in 3. If I'm not cutting it perfectly, it won't ring. And then the 5th. Those are all present in that sound. And just as an aside, the tone of a note is determined by how loud those partials are. So if I was to pluck right here, we have a kind of a pure sound because there's no higher partials, or very little higher partials. But if I start plucking down here, it's more of a whiny or a bright sound. That's because there's higher partials. There's more higher partials. They're louder. The higher partials are louder. So presence of partials determines tone. But that's all we're going to talk about with respect to tone with this. So that's the harmonic series. Basically, that's it. Partial series, right? 3 octaves. You got the octave, then the next octave is with the 5th, and then the top one is the 7th chord. Now we're going to talk about beats. When two frequencies are sounded out of the same, then the resulting note will be louder, the same, or softer. Now, some people might not think that it would be softer, but I'm going to show you a demonstration that shows that in a second. So if you have a waveform and you add another waveform at its exact same frequency, and the peaks line up like this, the peaks line up with the peaks and the valleys line up with the valleys, they're going to add together and they're going to make just a louder note. But sometimes you get a note and the same note, another note with the same frequency is played that has the peaks lining up with the valleys and the valleys lining up with the peaks. And when you add those two together, you actually get a softer note. And I want to demonstrate this for you. So now what we have here are two tone generators. And what we're going to do is show you that sometimes when we add two notes together that are the same frequency, they can actually be quieter. Two sine tones. I'll play one and then the other. And then every time I press play, it will start a new one. But sometimes it's quiet. And sometimes it's louder. And sometimes it's almost gone. It takes about 40 times before I actually get one where you can't hear it at all. I'm just playing, tapping away. Hear that? It's almost gone. And that's because the peaks and the valleys didn't line up. That's what happened on that one. And that can happen sometimes. And you might be, this is an argument for why unisons need to be carefully tuned pure. You can't just say tune in unison as pure as you can make it, because sometimes it gets, the two frequencies of the strings are exactly the same, but off a little bit. We say out of phase, and the result is a very quiet note. So if the two frequencies are different by a tiny bit, then the waves go from lining up to canceling out, like this. And what you end up with is a pulsation of sound, of volume, a pulsation of volume, loud, soft, loud, soft. This is what a beat is. And the beat frequency is just the difference of the two frequencies. So using those two generators, we can demonstrate by putting one at 440 hertz. And now the resulting beat will be 1 hertz. And that's a beat. Simple as that. Pretty basic. All right. Now let's go on to coincident partials. Remember our harmonic series above D3? Well, what if we had another series above G3, for example? If you look at those notes, you can see that they line up. Here's a note that belongs to both series. That's called the coincident partial because it belongs to both series. We need to know coincident partials for all common intervals if we want to orally tune pianos well, because that's where the beating is occurring. When an interval is not in tune, it's because those two frequencies aren't the same. I shouldn't say not in tune. It's not pure. When an interval is not pure, and we'll talk later about pure, wide, and narrow, but when an interval is not pure, that means that those two frequencies are not the same. And we often tune intervals in the piano that are not pure. So we need to know where that beating is occurring. If you don't know what the coincident partial is, you won't be able to know where am I listening. Now you could figure out each interval's coincident partial. You could figure it out, each one, by looking at the partial series, figuring out all the notes, trying to figure out where they line up, or you can just memorize them. And I'm going to make a table for you, and then you can just memorize that table. So some common intervals that we use in piano tuning: the major third. The coincident partial for the major third is where the notes line up, and in this case we see it's right here. This is where they line up. So how could we figure that out just from the major third? Well, it looks like it's just 2 octaves above the top note. So that's how you figure out the coincident partial for a major third. For a perfect fourth, it happens to be 2 octaves above the bottom note. For the fifth, it's 1 octave above the top note. For an octave, we actually have a bunch of them. The first one happens on the top note of the octave, the second one on the octave above the top note, the third one octave plus a fifth above the top note, and the fourth one is 2 octaves above the top note. So those are coincident partials. We'll talk more about these in sections 9 and 10. Now let's talk a little bit about pure, wide, and narrow intervals. If the coincident partials have the same frequency, so back here, if any of those pairs of intervals had the same frequency, there wouldn't be any beating. And we call those intervals pure. If intervals beat, it's because the coincident partials are acting like out of tune unisons. That's it. It's just like two frequencies that are close but not the same. If the coincident partial doesn't beat, it means that the interval is pure. That's a definition of a pure interval. So just to demonstrate, consider this fifth, C1 and G1. C1 has 3 partials, the octave plus the fifth, that's C1, C2, and G2. Now G1, if we just look at the 2 partials, the first one G1, the second one G2, we can see that they line up at G2. And that's the octave above the top note, from the table before. If both of those partials are exactly the same frequency, we say that the fifth, C1, G1, is pure. But what do we say if they aren't pure? Or they aren't the same, I mean. What do we say if the 2 G2s are not the same? What if the top note is higher? What if the top note is lower? What do we say? Well, if the top note is higher, we say the interval is wide. If the top note is lower, we say the interval is narrow. So I'm going to be using this to show you what wide and narrow looks like. This is wide, and this is narrow. This is pure. When the fingers are parallel, it's pure. Notice that you can have a wide interval by raising the top note or lowering the bottom note. Both of those actions produce a wide interval. You can also have a narrow interval by lowering the top note or by raising the bottom note. Both of those actions create a narrow interval from pure. I was starting with a pure interval. Right? This table just repeats what I just told you. When you take the top note lower, it's a narrow interval. If you take the top note higher, it makes a wide interval. Take the bottom note lower, you end up with a wide interval. Bottom note higher, you end up with a narrow interval. That's about it. That's about all we have for pure wide and narrow. We'll talk more about them later when we talk about check notes and how to measure intervals. But for now, we're going to go on to equal temperament. So with equal temperament, we can describe this very easily by starting with A0 at 27.5 hertz. Now, the multiplier to produce an octave is 2. We just multiply the frequency by 2 and we get the frequency of the note that's an octave above. So in this case, 27.5 multiplied by 2 is 55. Keep going, there's multiplied by 2, and then we get here at A4, which is 440 hertz. That's the standard pitch of all instruments. Keep going, we get to the top A, which is 3,520 hertz. We got there by producing 7 octaves, okay? But we can also start at A0, and get to A7 using fifths. To make a pure fifth, we multiply by 1.5. That's a pure in-tune fifth in equal temperament with no stretch, which we'll talk about later. So there you multiply by 1.5 and you get these numbers. You just keep going through all of them. And notice that we're making fifths, right? But the only fifths that are different colors are the fifth B, F sharp right here. This one here, we already talked about the pictures. All the other ones are the same color until we get to the B flat F. That's the only 2 fifths that are mixed colors, and all the other ones have the same color. And when we get to the top, we end up at 3,568. We overshot the octaves. So if we go from A0 to A7, with 12 pure fifths, we get 3,568. If we go from A0 to A7 by producing 7 pure octaves, we get 3,520. These are not the same number. You can't have both the octaves and the fifths pure. So what do? Well, we're going to choose to have the octaves as being pure. And that means all the fifths have to be narrowed. They have to be narrowed. So here I kind of demonstrated, I showed you how all the fifths are getting narrower and narrower, and the resulting A7 is getting closer and closer to 3520. So what we just did, we had to narrow all of those fifths or temper them equally. We equally tempered all of them, and we ended up with 3520. So that produces this following table, which is very important to memorize if you're going to tune pianos. One is that the fifths are all narrow fifths. And the inversion of the fifth, if you remember we talked about, is a fourth. And that is wide, because you have your narrow fifth and your wide fourth. If this is the octave, right? If this one here is the octave, then you have a fifth here, which is wide, narrow I mean, and the fourth is wide. Inversion, opposite. The major third is wide. It just turns out that way. And the major sixth is wide. But you remember what the inversions of the major third and the major sixth were? Minor third and minor sixth. That's why those are narrow. So these intervals, it's very important that you memorize those. To know that the major third, major sixth, and the perfect fourth are wide, and the minor third, minor sixth, and perfect fifth are narrow. But how can we know what size a piano's intervals are? How do we know? And how can we tune these intervals to these sizes, right? Well, these intervals are very wide or very narrow. It's easy to tell that they're wide or narrow. But these ones, these are near pure intervals. There's hardly any beating in these intervals. And it's very hard to tell if they're wide or narrow just by listening to them. We have to use check notes to determine if these near pure intervals are wide or narrow. Brings us to the next section, check notes. So you remember when we talked about the coincident partials? Right here we've got the perfect fourth, D3, G3 with a bunch of partials, and there's a coincident partial right there. Let's look at it this way. So here we have a perfect fourth with coincident partial. 4-3 it's called. Now, the way that these are shown, it's a pure fourth because it's showing that the two coincident partials are the same frequency. But in this case, I raise the top note. That makes it wide. But here, we've got the top note going down and it's narrow. So the top note is lower from pure. Lower from where it would be, need to be to make a pure interval. So we call it narrow. Wide and narrow. And we can test the size with a check note. What is a check note? It's a note that shares the coincident partial of the interval. And the most commonly shared partial is the fifth partial. We're going to use a check note that shares its fifth partial with this interval's coincident partial. So what is the coincident partial? Well, if we go up the harmonic series from D3, we get up to D5. Same thing with G3, D5. D5 is the coincident partial, so our check note will be D5 with the fifth partial. But what's the fundamental? To find that, all we have to do is go down 2 octaves in a major third. That's the distance of the fifth partial. You go up 2 octaves in a major third, you get the fifth partial. Go from the fifth partial down 2 octaves in a major third, you get the fundamental. So in this case, it's A sharp 2. So now we know our check note. But there's a few little things about the check note that have to be observed. First, the check note is set flat if it isn't already, and it should be beating about 4 to 5 beats per second. Not too fast, not too slow. Otherwise, it's not useful. So here we have our A sharp 2 flat from pure of both the D3 and the G3. And now the check note will measure how sharp of pure each interval note is. How sharp of the fifth partial each interval note's coincident partial is. That's the pink arrows. Second rule, you play the check note with each interval note separately. Sometimes people get confused and they play the interval notes together. No, when you're using a check note, you always play the check note. So in this case, we would play the major third and the major sixth. But you don't even have to know that. You don't even have to know you're playing a major third and a major sixth. All you have to do is play the check note and each interval note alternately, listening to the speed of the beat. So in this case, we might hear a la 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 la, and this could be la 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 la. You see? The top one is slower. And in order to determine the size of the interval, you need to be able to tell which one is slower. So in this particular case, we are able to determine that the test for the fourth is the major third, major sixth test. And to determine whether the interval is wide or narrow, you just have to remember that slower means lower. And in this case, the major sixth is slower, And the major sixth was measuring the top note. So top, slower, means top, lower. So we have a narrow fifth. That's a narrow fifth. Major sixes on top, top, lower means narrow. And so we can show here on the piano the fourth with the coincident partial being 2 octaves above the bottom and the check note being 2 octaves in the major third below the coincident partial. So the check note will always be 2 octaves plus the major third below the coincident partial. But sometimes, all the time maybe, it can be easier to memorize a simpler interval. So in this case, yes, the check note is 2 octaves in a major third below the coincident partial, but it's also just a major third below the bottom note. So that's how we memorize it. Coincident partial, perfect fourth, major third below the bottom note. And we just play that coincident partial with each interval note listening to the beat speeds produced at the coincident partial and compare. Slower means lower. So I'm going to go through all the common intervals that we can use to tune the piano. I'm not telling you how to use them, but I'm telling you what they are. As we just showed, the perfect fourth, the coincident partial is 2 octaves above the top, and the check note is a major third below, and that's the test, major third, major sixth. The fifth, you go down a major sixth. For the octave, we have 4 different ones that we talk about. So these next 4 different octaves, partials that we look at, are all going to be using the C octave. So in this case, the 2-1 octave, the coincident partial is the top note, and we go down a major 10th, which is an octave and a major third below the bottom note. Then you have your 4-2 coincident partial. You go down a major third from the bottom note. The 6-3, you go up a minor third. And the 8-4, you go down a major third from the top. Now, these next intervals are compound intervals that we use in the system I'm going to be teaching and talking to you about this weekend. The 11th, which is an octave, and a fourth. That's what the interval is, but the coincident partial is an octave and a fifth above the top note. And the check note is a minor sixth above the bottom note. For the 12th, this one's a little bit easier because the coincident partial is the top note. It happens at the top note, and the check note is major sixth below. The 19th, same thing. Top note is the coincident partial, and the check note is a minor third below the bottom. And then we have 2 more that I want to talk about. The 22nd, which is 3 octaves. Again, the coincident partial is the top note, and the check note is a minor 6 above the bottom. And finally, this one, which is a nice interval that is produced when we use this system, the Go Ape oral piano tuning system. That's the perfect fourth. That's pure at the second coincidental partial. So that coincident partial is 3 octaves above the bottom note. But it's quite amazing when I found this out, because I didn't really realize it until it happened, that we've got a pure fourth. Now the fourth is kind of like it's a bit of an interesting interval because it does beat quite, like, it's almost pure, but it's beating a lot faster than the fifth. And on one hand, you might be thinking, oh, it's kind of noisy, that fourth. But on the other hand, at the second coincidental partial, it's actually pure. There is no beating, if it's tuned this way, that we're going to show you this weekend. That brings us on to inharmonicity. So I just wanted to bring this back to your attention. This D3 here, with all those frequencies there, those were the harmonics. Remember we talked about harmonics? Each frequency was a multiple of 150. I also said that we don't find this in the piano. What we find is more like this, where the partials are a little bit sharper. We call that the partial series, not the harmonic series. And the reason why these frequencies are not harmonic is because of something we call inharmonicity. The thickness and the stiffness of the strings produces these higher partials that are sharper than what we would normally expect if we were just thinking ideally. Notice that each of the partials is slightly higher than the harmonic. So instead of 300, we have 301. Instead of 450, it's 452. Now remember this octave with all those multiple coincident partials? Notice where the partials line up. They line up at these partials. We can show these coincident partials like this. The 2-1, the 4-2, the 6-3, and the 8-4. In this octave, each of the partial pairs lines up perfectly. We have simultaneously produced pure 2-1, pure 4-2, pure 6-3, and pure 8-4, no beating at any of those coincident partials. But this is not true. This is not what we find in a piano because of inharmonicity. Because each of the partials are slightly sharper than the harmonics. We have something more like this. This is how the partials kind of relate to each other. If you look at each of these pairs, we can see that the partial of the top note is always lower. What does that mean? If the top is lower, we got a bunch of narrow intervals. A narrow 2-1, a narrow 4-2, a narrow 6-3, a narrow 8-4. So it's not too much of a jump to imagine that if we're going to have this octaves that sound at all good, we're going to have to stretch it. So it's going to be stretched from what we would expect, just doubling the frequency. Something like this. Now, A4 is the source frequency for tuning pianos when you tune by ear. So all notes above A4 will be higher than equal temperament if we're tuning the octaves to sound good. And all the notes below A4 will be lower than equal temperament if the octaves are going to sound good. Consider all these A's on a piano. And all these frequencies created when we created equal temperament by keeping the octaves pure. Remember that? These were the frequencies that we ended up with, 3520 on top. Now let's plot these frequencies on a graph. It's pretty simple. This is the graph of equal tempered frequencies with no stretch. We'll talk about stretch a little bit more later. But because of inharmonicity, the octaves sound better when the notes above A4 are higher and the notes below A4 are lower. Something like this. Is this what really happens though? Well, it turns out in 1938, a physicist named O.L. Railsback, I missed an S there, published a paper in the Journal of the Acoustical Society of America, and it's still going. This is the journal. He called it A Study of the Tuning of Pianos. And what he did was very simple. He just measured the strings of a finely tuned piano. And this is what he found. Does that look familiar? It's the same graph that we just produced. Higher notes in the treble, lower notes in the bass. Now each piano has its own stretch, and tuning a piano well depends, among other things, on how well you can tune the stretch to match the inharmonicity of the piano. There's different kinds of inharmonicity. Each octave is stretched. But how do we define how much the octave is stretched? How do we define that? This is where we'll talk about octave sizes. Remember this octave? We define the octave size based on how the partials line up. If they line up perfectly, we say that octave is pure. So this would be a pure 2-1 octave. This would be a pure 4-2 octave. This is a pure 6-3 octave, and this is a pure 8-4 octave. We can also define a single octave size, by the size of the other impure partials. For example, consider this pure 6-3 octave. It can also be named by its other partials if we consider how far off the partials are from pure. For example, if we look at the 2-1, the 1 is the top note. It's on the top note, that red 1, but it's a little higher than what would make it pure. That makes it a wide 2-1. Same thing with this 4-2. The 2 is a little higher, and the 2 belongs to the top note. So that makes it a wide 4-2 octave. And up here, for the 8-4, the 4 belongs to the top note, and it's a lower. So we have a narrow 8-4 octave. But what's the best size? Just which size is the best size for a piano? The 2-1? Somewhere between the 2-1 and a 4-2? The 4-2? Somewhere between the 4-2 and the 6-3? The pure 6-3? When I say the 6-3, I mean pure. Somewhere between a pure 6-3 and a pure 8-4? Or a pure 8-4? What's the best size for an octave? And how do we measure them? Or tune them to these specific sizes, even if we did know what was the best size? That's what we'll be talking about in the second class, measuring inharmonicity.